1 over the resistance. Some raised to what? The whole thing raised to some. What's the negative one? But I included that in the, I said 1 over resistance.
Okay, let's get started. So PMOS is good at passing what?
The VDD.
Yeah. And NMOS is good at passing
ground.
And in order to pass both signals, we prefer a transmission gate instead of a pass gate, right? Here's a transmission gate of PMOS and NMOS. Yeah, makes sense?
I like it too.
Yeah, and you need to turn on the PMOS by giving a 0, and you want to turn on the NMOS by giving a 1. So if you want to turn on the transmission gate or TG, this is PG. Here's are the two signals you want to give to the transmission gate in order to pass whatever here to here. So if you run the simulation, I think this is one of the homework assignment. This is NMOS, right? And this is input. What are expecting for the output if this is a signal being injected into either source or drain? Right? It is on, which is a given condition. Definitely, you have to keep it on in order to pass anything, right? This is an NMOS gate. It's not a transmission gate. It's just a pass gate, one of the two types of pass gates. If this is input, what are expecting for the output? So NMOS is good at passing what?
Ground.
Yeah. So could you pass ground to it? Yes.
Yeah.
Could you pass 1 to it?
No.
No. So how much loss? VDD minus VTH. Wait, what's the voltage amplitude here? Right? You're trying to reach VDD, but you cannot because you lost VTH here. That's why the amplitude here is this. And the margin here is VTH, right? What are PMOS? Input. I haven't simulated yet, but I put on a homework assignment. I'm just curious, see what you guys can do. So I'm asking you guys to run the simulation to show this hypothesis. You can do it. You can.
You say that now. Just wait till you have an office hours.
I'm going to run the simulation after showing this page. How about that? So what about PMOS? PMOS is good at passing grounds. No, VDDs, right? So it is not able to pass the whole ground, but it is able to pass VDD. So the voltage here is VTHP, right? It's losing a threshold voltage. The run, I can do it really quick, so I'm not wasting too much time from you guys. C. It's okay to do it here because I'm saving office hours. Do it either way. Let's do NMOS. What about that? Just copy and paste this one. PG. Let's see. What I'll do here is should delete that one. Okay. So I'm going to copy this guy because it's a pass gate, so I need to give a 5 volts to keep it on. And this one, I need a pulse, right? Pulse with initial 0 volts, V on 5 volts, T delay 0, T rise, just make it really sharp, rising edge, and 1 pico as well. T on, let's do 1 microsecond, 2 microseconds for the periods. Okay, now I'm gonna move this one down here. And, delete that wire, don't really need it. And because it's NMOS, so where should I connect this body contact to? So, no, this is body, right?
Oh, wait, NMOS.
Yeah, so it's ground. And because we are feeding signal to the source, for example, it's symmetric structure, so it doesn't matter. And this one is, do we need the power for it? I don't think so. It's a pass gate, just passing the signal over to the other terminal, right? We don't actually need the power. Is that correct? And then if we name this one as V signal, here's a signal. I just feed the signal to here. Oh, do we need the power? Yes, we do. Friday afternoon again. I'm going to do a 5 volts DC and rename it as VG. Okay, and I'll copy this one here. So it's always on, right? It's always on. Pass gate is always on, which is desired. And then we just measure the V out, or the probe the V out here. Run it. Oh, it's operating point. We don't want to do operating point simulation. We want to do what? Yeah, transient analysis for that 1 microsecond. For the 2 microseconds for the period, let's show 10 microseconds, 10 periods, 5 periods there. So it's 10 microseconds. And run it. Signal, right? And show 6 volts here so you can see the logic 1. V out. What's happening? What's happening here? Come on, guys. What's happening? Does it make sense? Answer this question first. Yeah. Why? Yeah. Let's measure it and see if it's see if that's true. So I got voltage here. Where's the second one? Where's the second one?
Like right at 5 microseconds.
Oh, here. But both of them are measuring. So if I click the first one, then I click the second one, it doesn't work. But I can do it separately. So what's the voltage here right now? Vertical voltage, 3.9. Yeah, there are a little bit more loss compared to 0.8, right? It's about like 1.1 volts loss. Let's slow it down and see if that's a speed issue here. I don't think so because it's fully charged. It's getting flat. Let's slow it down for 10 times. Run. Is it getting better? Oh, 4.0, slightly better. But if we move it to the right hand side, it's getting closer, right? Let's slow it down further to charge up, right? Let's do 1,000. think it's getting there. See? It's a successful simulation for that. So I think the homework assignment is asking you guys to do this one and the PMOS and the transmission gate. So you can compare the differences. Make sense? Mm-hmm. Okay. Don't forget to connect the body to the correct places, even though it looks odd. But PMOS body should be shorted to where? Highest potential. Just put a VDD there, right? For the NMOS, just put the ground there. Cool. And something we didn't cover last time for the inverter is a switching point. It's a very interesting topic to talk about. So the inverter switching point. So right now, if I let you guys to draw an inverter schematic, could you do it? Just now looking at the notes. Really? Could you? Yeah, let's do it. PMOS first, right, on the top. Why do we put the PMOS on the top? Passing VDDs, right? So it's in charge of passing VDDs. And NMOS at the bottom. And the gates should be shorted together just because it's just one input. And here's VL. VDD ground. Okay? And one thing you need to understand here is if your V in, if I'm plotting, remember last time we plotted V in and V out. So the x-axis can be V in or V out. It's just a voltage. I'm just plotting a voltage. I can probe, the spice can probe both of them to show both of them on the one plot, right? So in that case, the x-axis is V in, the y-axis is also V in, right? So when V in is 1, V in is what? Yeah. When V in is 2, when V in is 2, V in is 2, right? So it's like that. Make sense? So if I plot V in when I'm doing a V in DC sweep, I'm going to get this. What about VL? So when V in is 0, VL is? When this is 0, PMOS is on or off? On. This one. Off. So this point is being pulled up to VDD. Be aware of the terminology I use here. Pulled up to VDD. Okay. So at the very beginning, you have 5 volts for VL. And then whenever you get larger than V in, it starts falling. It won't be a super sharp. There will be a little slope here. Okay. This is what you're expecting to get. It's not a perfect device. It's not going to switch at one certain point and then there's no room, just super steep and then going to 0. No, it's not happening like that. It's going to be a slope here. And this point is called the VSP. It's a switching point. Why is this important? It's just an inverter. It's one of the logic gates you have in logic, in digital circuits, right? But you have all the other logic gates like AND gate, NAND gate, NOR gates. They are similar. They are being built in a similar way. Whenever the logic is being flipped, you are going to see a switching point at some point. They're all logic gates. So why is this important? And what's the ideal switching point you can think of? So this comes down to the benefit of using digital circuits, right? Why is digital circuits or digital TVs are more higher resolution than analog TVs? Oh, before you were born. Huge boxes.
Oh, those guys. Okay.
So scanning the whole monitor. I forgot the name of it.
CRT?
Maybe, yeah. So why digital TVs are more clear or higher resolution than analog ones? So they are more resistant to what?
Noise.
To noises. Okay? And that's where makes the digital gates resistant to noise, because it has a threshold here. The switching point is 2.5, so anything lower than 2.5 is considered as 0. So I have a lot of room for noises, right? If there's a little spike or a surge up to like 1.2 volts, still 0. And if you are sometimes getting a lower voltage because it's not able to charge and discharge or drive that load, so the 5 volts is being lowered down to like 4.2 volts, it is still logic 1. It's not going to affect anything, it's still 1, right? So in that case, what's the ideal switching point can think of? Perfectly, it should be 2.5, right? If I have 5 volts logic, then somewhere in the middle will be the best situation. So when you're designing the digital gates, not just the NOT gate, right? This is NOT gate, which is the inverter, but also the other non-gate NOR gates. You have to consider the switching point if you're trying to optimize the design. Okay. So one quick question here I'm not just telling you the conclusion here, I'm just letting you guys to think about it. You have a width and length here, right? Ratio for the PMOS and NMOS. And the square law equation has this one in there as one of the parameters. Kp, either N or P, doesn't matter, right? So W over L, VGS or VSG, V minus the threshold voltage. Let's just use N here. Okay, so if you have a larger W over L ratio, you're going to have a larger what? Current. So larger W over L means stronger or weaker, transistor. Stronger, why? More current, like bigger pipe, more water.
Yeah, I just told you.
Okay. So for example, ideally, if they have the same strength, like push and pull, okay? You have a PMOS trying to pull the current up, and NMOS at the bottom trying to pull the voltage down to ground. They're competing, right? So if you have a stronger PMOS, which means you have a tiny NMOS, but you have a huge PMOS, where the switching point of this is going to shift.
No, it'd be higher one, right?
So if you have a stronger PMOS, so for example, this one is 2.5, okay? Right, so in the middle, whenever they have a equivalent strength. Okay. And if you have a stronger PMOS, start with a stronger PMOS. So whenever V is 0, it's always on, right? There's no doubt on that. Okay. But whenever you are increasing V in, you are shutting this off, right? But if you have a stronger PMOS, it's going to struggle for a longer time. We'll keep it on for a longer time because it's strong. Even though you are trying to shut it off, but it's huge, you just shut off 50% of the width or whatever the electrical current flowing in there. It still has 50% of the width conducting current. It's still stronger than the NMOS, still on, it's still conducting, still pulling that V out up to VDD. So is the switching point going to shift to the right or left?
Right.
Yeah. It's going to delay the switching to the stronger PMOS. And if you have a stronger NMOS, a weaker PMOS, and whenever you increase V in from 0, right, because it's strong, so it's going to turn on NMOS earlier, right? It's strong. Whenever you give a little bit voltage or a less voltage than 2.5, it is able to turn it on. So it's going to switch earlier. Okay, stronger NMOS, right? And you can run the simulation easily in LT-SPICE. You build an inverter, you change the width to length ratios, and can compare the switching point.
The V out doesn't change, right?
Yeah.
Why?
Yeah.
Okay.
Yeah. That's right. Good question. And how could we calculate the switching point voltage in order to design the size of the NMOS and PMOS? Right, now we know it's going to affect something, right? It's going to affect something. So we can design it to let the switching point right at 2.5 volts, ideally. Let's see how do we calculate it. Still the inverter, so whenever it switches, what is this voltage? Yeah, Vn. What is this voltage?
Yeah.
What's happening here?
Vn equals VL.
Is that correct? Yeah. Right? And we name that as switching point. When Vn equals VL, it is a switching point. And let's see. When Vn equals VL, what about the current flows through the PMOS and NMOS at that time, at that moment? Y is equal. Y is not equal. Are they always equal to each other?
No, because the PMOS is bringing down VDD, and then the NMOS is bringing up ground. So wait, does that just make it equal?
No, it's a branching circuit, right? So I mean, like, I don't know. This is of my pay grade.
Wait, I have to think about it. Why, when it's at the switching point, the current equals to each other? That's what I wrote here. So in the meantime, so when Vin equals to the switching point, Vin equals VL, and the currents are equal. To look at the textbook and see what's the explanation over there.
Oh, the current is equal?
Yeah.
Oh, my first guess. Nice.
So you can use the square law equation for the calculation. Right? Remember KPN over 2, no, KPN over 2 W over L. So this part we rename as beta N, right? And KPP over 2 W over L, and this part is beta P. And because current in the two transistors are equal, so beta N over 2 VGS minus VTH N square equals the current in the PMOS, beta P over 2 VSG minus VTHP. So VGS, because Vin equals VG, right? And this is ground. So VGS is from here to ground, and Vin is also from here to ground. So whenever it reaches a switching point, Vin equals VL equals to VSP. So we can substitute this with VSP. So it becomes this. What about the VSG? What about VSG here? Because Vin is VSP, right? So VSG is VDD minus VSP. Right? Mm-hmm. So in the square law equation, we use VDD minus VSP minus VTHP for the current, and they're equal, and these two are canceled. And then I move beta P to the left-hand side. You got this here, move it over here, and move this over here. We want to move it over there. Yes, you'll do. So this equals VDD minus VSP minus VTHP, VSP minus VTH. Right. And square root on both sides. We are asking like What about this is negative? So you cannot directly do a square root on both sides and make them equal. Can these two be negative? Hmm? No, right? Yeah, these are always bigger than these two, right? And this is always bigger than this one. We are good on that. And let's see what's next. How do we calculate VSP? Yeah, you have to move things around. Let's see. So VSP, just one variable, you can definitely calculate for it. Then just do it. Move this here. We're getting 1 plus. Move this here.
And how did you get 1 plus?
You factor VSP out. It's got a 1 here.
Oh, I see.
And this plus this one minus this is correct. And now I got VSP here. So VSP equals VDD plus
Do we have to memorize this one?
no, you don't have to memorize it, right? Do you have to memorize it? If you know these two equations, you put them together, so you can directly get here yourself, right? Did you?
If we're relying on my mediocre algebraic ability, no.
Let me see if this is correct. It is. Okay. So here's example. Estimate beta n and beta p, so the inverter's switching point is 2.5 volts. So if this equation is given, right? And these are just constants. So beta and beta p are the only two variables.
I thought beta, oh wait, no, because beta.
Yeah, beta is yeah, width and length, right? And this is constant as well in beta. So it's just width and length. So find it out. I mean, based on the KPs, right? Because NMOS and PMOS have different KPs. So for the KPs we have for the 1 micron technology in LT Spice, we can find out what's the ratio of beta N over beta P in order to make a 2.5 switching point. So I think the final calculation is you just use this equation that equals 2.5 volts, right? Because this is a switching point you want to use. And then put in this equation and calculate for this. So this equals, what do I have here? 1. Close to 1. It's not really 1, but very close to 1. So which means, so beta n, let's use 1 here. So beta n equals beta p, right? Equals kp n w over l n, right? Equals kpp w over l pp. What's next? because you remember KPP is 40, right? And KPN is 120. Let's put a unit here, microamp per voltage square. Microamp per voltage square. Because KPN is 3 times KPP. And put in here. So you can cancel out KPs. And you are getting 3 here and 1 here. So 3 Wn over Ln equals Wp over Lp.
Why is the KP for the NMOS so much bigger than the KP for the PMOS?
Because the holes are moving slower than electrons.
Okay.
The Kp is the function of mobility and capacitance. It's okay. I've asked this for twice or 3 times. So the best way learning is repeating or teaching, right? I'm going to repeat. And you're going to remember this. So eventually we got here. I mean, I just want to ask you if this makes sense. If you don't have a switching point to be 2.5 volts, you need the PMOS to be larger or the NMOS to be larger? PMOS to be larger here, right? Why? Move slower. So you need to make it larger in order to have the same strength as the NMOS. Okay, so it's 3 times larger for the PMOS. Do you have to modify L here? Why? It's just ratio, right? Like the sheet resistance, you don't have to modify both. You just modify one. And the lens, you want to use the minimum lens you can use to save space on the chip.
Does this work for any? So is the ratio 3 times for the PMOS for any switching point that's half of your VDD, or is it?
It depends on the mobilities.
Well, right, but like if we have these mobilities.
Yeah, PMOS is always weaker than NMOS, no doubt on that. But how many times? It can be 3 here, but can be twice, can be 4 times. I don't know for other processes. It should be somewhere around that. But what you should know is PMOS is stronger. No, NMOS is stronger than PMOS because the mobility of electrons is higher than holes.